Hello, I am Sombit Day. This summer, I was working under Professor John Dolan and Chen Fu in the Argo AI Center for Autonomous Vehicles at Carnegie Mellon Institute of Robotics on my project of shape completion of objects, particularly for autonomous vehicles. We can't estimate the shape of a vehicle and differentiate among different vehicles on the road just from the raw LiDAR and camera data. Knowing the shape of the objects in the scene helps the ego vehicle to have a high level information of the surrounding, which can be used for path planning in urban scenarios. Previous research also confirms the improvement in object detection using shape completion. The main challenges for shape completion is the lack of ground truth annotation of objects, which makes it difficult to use deep learning models for shape completion. Also, the raw LiDAR data is sparse and noisy. To tackle these challenges, we propose a three-stage pipeline for prediction of vehicle shape. We receive RGB image and sparse LiDAR data as input. Firstly, a pixel level segmentation is carried out on the image. Secondly, the depth image is also obtained using features from both camera and LiDAR. We used these densified objects as the input to the shape completion network. The output of the shape completion network is a 3D shape of the objects. Here is a data flow diagram of our pipeline with results of image segmentation, depth completion, and 2.5D shape representation of the object. Image segmentation. Image data is segmented into three classes: cars, pedestrians, and background. A unit architecture is used to segment the images. Skip connection is used to transfer the fine-grained details to the output. Segmented image is used to mask out the relevant objects in the scene. This approach reduces the noise when compared to the traditional 3D bounding box approach of segmentation of objects. Depth completion. The raw depth image obtained from LiDAR is very sparse. We use a self-supervised approach utilizing geometric relations between the nearby images in the sequence while training. This approach allows us to train the model without ground truth annotation. Here is an overview of our approach. The network maintains consistency between the two images during training. The results of depth completion network is shown. Using the output of the depth completion, we can reproject the image points into the world frame using the intrinsic camera parameters. The aim of the shape completion network is used to interpolate between 2.5 dimensional point cloud data to 3D shape of the object. For shape completion, we use a variational autoencoder architecture. We use two models, namely shape prior and shape inference model. A shape prior network is trained on the synthetic dataset of CAD files. Shape inference model is used to transfer the learned features from the synthetic dataset into the real-world scenarios. The observations from the KT dataset is used to train the encoder to learn the embeddings into the latent space. We retain the decoder from the shape prior model into the shape inference model. In short, we can summarize our approach using these outputs. Firstly, we take the sparse LiDAR data as the input. We densify the data using depth completion. Using shape completion, we can predict the shape of the object. The output of the shape completion is in occupancy grid representation, where every voxel has a probability of being occupied. The occupancy grid is converted into a surface-based representation using surface triangulation meshing. The core novelty of our approach is the usage of image information along with the sparse LiDAR data for shape completion of objects. Our approach tends to generalize better than the existing approach using sparse data, as the RMSE values are lower even though the number of points are higher when compared to the previous approach using sparse LiDAR data. Future work involves integration of our pipeline with object detection and to insert the objects within the LiDAR scan. I would like to thank CMU RISS program for sponsoring this opportunity. I want to express my gratitude to Professor Dolan and Chen for their mentoring and guidance throughout the summer. I would also like to thank Professor John Dolan, Mrs. Rachel Boshin, and all other RISS sponsors for making this experience possible.